Hello and welcome to this incredibly long overdue video. This one going over the new updated version of the Unused Voyager Tricorder, now dubbed version 2.5. Firstly, I want to apologise for the slow release of videos. This is because of several things. Firstly, this rung of tricorders took a lot longer to build than I anticipated, and I have been dealing with a lot of difficult personal grief due to my father's cancer diagnosis and more recently his passing. But I really wanted to get this video out, so let me introduce to you the new Unused Voyager Tricorder version 2.5. Outwardly, this tricorder is nearly identical to the last version, though some changes are clear if you look really closely. Some of these changes were done with the aim to make it easier to assemble, but more importantly easier to disassemble and repair if anything goes wrong. So I rearranged many of the components and added another PCB that's more dedicated to power. I'll go into more detail on that in a bit. I also changed the way this thing powers up. Before there was simply a switch that turned the thing on, but now I have placed a push button underneath the power button. This push button pulls power directly from the battery and sends it to both the enable pin on the main buck boost converter and to the Q-on pin of the charge controller chip. This internally enables the battery MOSFET of the chip, and this then powers up the main system power rail, which in turn goes through the DC to DC converter that powers the tricorder. As part of the startup routine of the tricorder, it reads the status of that power button, detecting if the power on was triggered by the power button or simply triggered by the display mode turning on. And that startup routine then latches the enable pin of the main buck boost regulator via a GPIO pin from the microcontroller. All this happens in the space of a few milliseconds, so to the end user, the tricorder simply turns on by pressing the power button. While this is nothing special, and in the grand scheme of things, computers and phones have been doing this for decades, I was rather proud of myself for implementing this inside a prop. Funny thing to note, the charge controller chip I'm using, the BQ24297, is the same chip used in some smartphones and DIY smartphone projects. So my tricorder is now more like a smartphone. In fact, one of the main reasons for the changes to the power system was to provide a cleaner, more simplified rail for the majority of the tricorder to run on, in the hopes to help with efficiency and battery life. However, this should be noted that the battery life overall has not changed in any significant way. And in the end, I also needed to reintroduce the TPS61023 to power a 5V rail just for the audio circuit and amplifier chip. This is the same DC to DC converter chip that actually gave me a lot of trouble in the previous version of the tricorder, but as this rail was limited to just audio and was so using a smaller amount of power, I felt it wouldn't be an issue, and for the most part it worked out okay, though when the battery is getting low the audio circuit does sometimes reset itself, which highlights this problem going forward. This will be replaced in a future version. One of the other changes I will make in any future version of this tricorder will be to the amplifier chip itself. The amp I'm currently using is an 8002A amp, a very common simple AB amplifier. The issue with this amplifier is simply the type. With it being an AB class, it uses a surprising amount of power, and I notice it does heat up after a while. While the temperature is nothing to really worry about, it does highlight that this current audio circuit is not efficient and actually draws nearly 50% of the total power used. So I found a replacement for a future version, a TPA2005D1. This is a D-class amplifier from Texas Instruments, and while the pinout is identical to the common 8002A, the IC uses a smaller package, so it can't simply be used as a drop-in replacement. A new PCB will have to be designed for this amp, which is why it's not already installed here. One of the biggest changes to the new design is how it's assembled. I wanted this to be something that could for the most part be taken apart to do repairs on if need be. This meaning the risk of having to literally crack it open massively reduced. And it's a good thing too, as you will soon see. So I'm actually recording this segment again because I recorded this yesterday, started editing it, and I realised I was and arming a lot, like that. So I want to try and do that less this time and try and get a bit more of a coherent video. There will be a few cuts between each section just to help me organise a little bit better and think more in the process of what I need to do. So here we have the tricorder, and I'm going to be taking this apart as best as I can. That being that I designed this to actually come apart to a certain amount. The tricorder can't be completely taken apart. Some things are still stuck in there, but the design behind this was that most of the electronics inside it could be repaired if they were to fail or go bad during assembly, and it certainly was the case while I was doing this large run of tricorders. So the majority of the PCBs are inside the main body. They can be accessed and are repairable. However, the big problem was actually the door, the electronics inside the door are sealed in. There was no way around that particular issue because of the way that the tricorder is designed. There's no obvious hatch on the prop, so I couldn't just put a hatch on here like I could with the back of the main body. And so once the electrics were in there, they're in there. And there was a case that one of them I did end up having to cut back out in order to repair. However, that was fixed, and that's all. You know, it's a lot of work, you know, to cut this out and then repaint it and refill all the hatch and whatnot to make it look reasonable. But luckily, that only had to do it to one of the tricorders. Though almost all the tricorders did have problems while assembling the electronics, as I probably showed you in one of my previous videos. So we're going to take this one apart, and hopefully I can show you, and hopefully I can say this without stuttering too much, though I already am struggling to. Anyway, okay, so after all that rambling, let's actually take this apart and have a look inside. To begin with, I need to take the hatch off. I don't normally recommend using something like this, but for me this is just handy, but it can scratch the paint around here like I've already done on my one. So hatch comes off, and inside we can see that we've got the battery, the speaker, and the main control board underneath. So let's start off by taking the battery out. So again, pulling on the tab releases it, and then pulling the cable out from the socket. The LCD and the main microcontroller are held in using a frame that's pressed inside the case. But in order to release that, I've got to first release the front section. To do that, there are two screws up here. These retain the front sensor cluster. We'll take that one out first. These screws can sometimes be a little bit fiddly to get out. There we go. So taking out the front sensor cluster, sometimes a little bit of extra prime on the side, there we go. Taking out the front sensor cluster, and that's it. A really simple PCB design, just the buzzer, the LED controller, the board-to-board connector that connects to the other board in there. I'll have a look at that a little bit more closely, and the LEDs, and that's pretty much it with this board. It is a very simple board. It's just mostly relaying stuff from the front here and the LED controller here. Put that aside. course I realise I am still umming and ahhing a bit, but hopefully it's not as bad as the one I did yesterday. Right, in order to remove this, we'll say we need to remove the front sections first. So there's another PCB inside here. This is the main power PCB inside there. That firstly gets pushed out slightly from here. There is a 1.27 IDC style connector that connects to the main board by a female socket there. Just get a little bit more light over via the socket there. It's also retained by a ribbon cable under here, so it's going to release that. Pull that out. So here we have the main power board. There have been a couple of fixes on this one. The one you can see there isn't actually required. That was me just trying to find out what was going wrong with this particular model a while back. But actually it wasn't a design fault, that was just me researching it. So that was corrected. The board itself, let's have a quick look a little bit more closely. So we have the LED controller, the battery controller, which I mentioned before, and the main DC to DC converter. That is for 3.3 volt, a 3.3 volt rail. This little hacked on capacitor is to help with the audio glitching problem I was having, and I mentioned earlier when the battery gets low, by helping to provide more power to the sys rail. It hasn't exactly worked, and that will obviously be something that I fix in the future, but this does help alleviate some of the problems. On the back I have a little hacked in resistor here. That is for the power on battery, the power on line between the microcontroller and the main DC to DC chip. I can't exactly remember why. I think it was for some kind of like current limiting stop feedback from the battery, but I can't be exactly certain. I'm trying to remember this, but God, well over a year ago when I put that fix in. So yeah, anyway, that is the main power connector. Oh, and of course that's the other half of the board-to-board connector that the front sensor cluster and this connect to. That will see it's a low-profile connector that's able to pass a load of different connections over to the two halves. Put that aside for now. Now, coming back to the tricorder itself, let's take the half of the frame out, which we can then get access to the main board. To do that, there are two hex nut screws that I just need to remove. My tweezers to help with this. Now this bit can be a little bit fiddly sometimes, as these frames can be a little bit fragile. It's just resin in the end, but hopefully that won't break while I'm doing this. So gently lifting that up and making sure that is all the way from the side. These are wedged underneath, then they hold in half of the display and board. The other half is this side. So it's partially pressure fitting stuff in, as well as bolting stuff down in order to help everything stay in securely. Okay, take this one out. There's a small retaining bolt here. Got to loosen this flat flex cable first, and we need to pull the speaker away from the side here because that's covering up this ribbon cable. So there's just some double-sided rubbery tape on the back of that to help against the uneven surface that it's sticking to. There's a ribbon cable here, and that is to provide the power and the channels for the library LEDs up at the edge, and we'll have another look at them in a second. So gently pull that out. Now with that loose, I can hopefully wiggle this out. Of course, doing it on camera never seems to work as well. Okay. Right. There we go. So that's now out. Let's quickly take the other half of the frame out first, and then we'll have a look at the main board. So just to remove 2 small screws on the inside here. The other. So hopefully this should now come up quite easily. There we go. And that is the other half of the LCD and main controller frame. These two go together, kind of like that, and then bolted. Yeah, that's the way around. And then they are bolted on each side there to hold it all together, and then that's obviously press fitted on one side, and this is bolted in on the other side, and that keeps the display and the main board locked inside here. We'll have a look at that in a few moments. Here we have the main board and the LCD display. Now, as I've mentioned before, the LCD display is actually cropped inside here. As you can see, it doesn't quite fill up the entire window. So in code, I've just basically, I'm not using the top portion of the LCD here. The LCD is just connected via this connection here. We'll remove that. This bit is a bit more awkward because probably could have designed a little bit of a better, bigger window in there, but that works. So now the LCD is now removed. That could be replaced if it ever got broken, and that hasn't really happened with these yet. I've had it happen on another project, but not on these. But yeah, that's now removed. Let's zoom in a little bit more and have a look at the main board. Right, so we have the main board, we have the main microcontroller, that's the STM32F103CB. We have the graphics chip, which is an FT810 from Bridgetech, or used to be known as FTDI. These two communicate to each other via SPI. It sends OpenGL-like commands to the graphics chip, which then renders out the commands onto the display. It could be things like display this bitmap here at this location. It can also be as simple as setting up dots or lines and whatnot. And obviously, using a large script of code, you can end up animating the UI as you like. The display chip sends out the display signal over RGB 656. Was it 85 or 868? I can't remember now. It's not full 8-bit. I think it'd be 868. I think. I need to try and have a look at the data sheet again to be absolutely certain. But yeah, it's only because this chip is not an 888 based chip. The display can handle full 8-bit, but this chip doesn't output it. The version above this does. But for what I'm using it for, that's really not a problem. We're not using it as an HD display here. This is purely a prop, and for the most part, most people won't realise the difference between the two if they're just looking at it, particularly on a user interface. Down here we've got the audio chip, so that's the main amp chip that I was mentioning before that needs replacing. We have the JQ, is it 5560 or is it 6650? It'll be written on there somewhere. Let's see if we can zoom in on that. Come on, there we go. JQ8400. There we go. That's the audio chip. Basically, that's a flash chip, and on there I've got various audio files stored, such as the scanning sounds and whatnot. And this just plays them back. It's a Chinese chip. Very bad data sheets that are barely understandable. But I managed to get something going with them, and in the future I might change it for another design, but for the moment I've got a bunch of these and I can use them for this, so that's not a big issue. And under here we have over here we have the micro SD card that holds all the assets. The graphics chip and the micro SD card are on the same SPI line, and they obviously well, because they're on the same SPI line, the microcontroller shares the data off the SD card and onto the graphics chip memory for basically to load the assets and bitmaps. Now we're going to have a quick look at what was actually my mistakes on this particular board. So we're going to firstly have to remove the micro SD card. I'm a little bit careful because it is a little bit awkward. I don't always want to come out if I choose my fingers. Okay, there we go. Okay, micro SD card out of the way. And the first thing you'll notice underneath there is a trace that I've added. Now that's just hot wiring onto the SPI clock pin on the micro SD card. And that's running across the back here up to the display. And the reason that is because the display also uses the SPI bus, but it's more like a bit banged SPI. It doesn't use normal SPI as a standard peripheral. But for some weird reason, between designing the board and sending the board out to be fabricated, the clock trace disappeared off the design, and I have no idea why. So I had to hotwire that one back in just so I can use the clock on the display. That is so I can then send data to the display to make the display run in the parallel graphic input mode rather than SPI graphic mode, which is part of the starting routine, which we'll go over shortly. The other little fix I had to do on this board, if very carefully look closely there, which is not the best position for it. On the other boards I actually fixed it further up here where there's a lot more space to deal with, but down here I had to swap the plus and minus lines of the USB that goes to the audio chip. In order to put the files on the flash chip, this emulates a storage device on USB, and that exposes the flash for me to put the audio files onto. But for some reason, even though looking at the schematic, I don't know why I did it. Even my own schematic, they're labelled correctly, but I just for some reason got the two lines flipped around, so I had to just hotwire the two fixes, flipping back around over each other. And because of the audio skipping problem I was having when the battery runs low, again I put another capacitor really close to the whole 5-volt DC connection or section here. Right, we're done with this board for the moment. Okay, here we are with the tricorder and the PCBs that are still inside it. These are glued in. They are mostly super glued. In fact, they're all super glued. And the reason why was because certainly in the short time I wanted to get this finished, and I say short time, I've been working on this a hugely long time, I couldn't figure out an easily removable way of holding these particular PCBs where they needed to go while fitting all the other components inside. So given that these were fairly low priority PCBs, being that there's not a lot to go wrong on them, and you know, sometimes they did, these ended up getting glued in. So what we have is, firstly, inside here, that is what I call the Voyager LED. That is the one that lights up the jewel at the top of the here. That's just an RGB LED that runs through the ribbon cable and then through this ribbon cable to the LED controller, I believe, on the power board. Another RGB LED here, and that's for the gel pack, as well as what I call the data spark LEDs inside this section there. Turn that light back on. And under here is the power button. That's embedded into the PCB itself, and it's backed up with super glue as well, just to help make sure it doesn't like break the solder joint itself, because if I just put all the pressure into the solder joint, it probably will end up being broken, you know, from pressing down the power button so many times. So super glue is there to back that up. And on here we have the LED array for the lib LEDs. That is the LEDs across the top there. Again, just a simple ribbon cable that presses down into that socket. Really fairly low profile, so quite simple for me to connect that into. And we have this other ribbon cable which is soldered on one side to the Met Bio Geo board. This board literally just holds the buttons, the few LEDs that are on here, and the power and UART pins here, as well as the Hall effect sensor, which detects when the door is being closed. Not when the door's closed, but when it's being closed. So as the door is starting to close, from around this point it will detect that the battery that it's being closed and begins the ratchet sound for it being closed early. This just gives it a little bit more of a realism with the ratchet sound triggering before it's already closed. So you know, before, when I just close it, it'll go, you know, do the ratchet sound once it's closed, and that just didn't work out. So that helps fix that little problem. And of course, the PCBs in there can't be removed because this is a sealed section. I would like to have had it something. I considered maybe having something here that can pop out, but I looked into it and I just couldn't figure out a way to make that really possible. At least with this particular design of prop. You know, in future props I can make something, you know, that I can make it just easily disassemble, but this particular thing, trying to keep this sort of sealed door design, didn't make it really easy. Right, I am actually taking little moments between each section because it's helping me gather my thoughts properly and plan exactly what I'm going to do. So here we are now. We're about to put this back together. I won't really talk too much because frankly it's pretty much straightforward. You see me take it apart, now let's put it back together. Shortly after this we will then go through some of the changes of the program and how I've rearranged certain sections of that. So to begin with, we need to put the frame back in first. Starting with this section, firstly it needs to slide up underneath the ribbon and behind the lib connector first, and there's a few angled bits that allow me to slip it behind there. With that in, I can then gently screw these hex bolts back in. The reason why I have to be a bit gentle is because the actual nuts that hold them in, they're just held in with super glue, and they don't need to take a lot of stress, but if you tighten this too much, that can just pull the super glue off the the thing, and yeah, they don't want to have to re-glue them back in again, which is a pain. Okay, they're still gently put in. We now want to put the main board back in. Firstly, let's loosen that a bit. Oh, no. Got to put the display back on first. Oh, okay. Okay, display first. Carefully feed that onto the socket. Okay, display on. Now push this board in. The top of the board hooks underneath the corner of the chassis. Display goes in its place. Loosen that again. The ribbon cable there. Tighten up. What? Already managed to lose one of the screws. Where did that go? Oh no, there it is. Okay. Put the screw back in the corner. That's needed in a moment. I'm going to carefully put this ribbon cable, lining it up to the slot. Only putting pressure so it goes into the slot correctly. Okay, can I move that back over here? The other half of the frame gets pushed down into this corner first, and making sure that is out of the way. Push down gently. And that's mostly secured. Need to put the SD card in, just realised. Do that in a second. These two bolts. Let's quickly put that in. Right. That's the main board secured in there with the LCD. Let's put the main power board in. It's going to be a little bit tricky. Firstly, I need to open the hatch on the ribbon socket and carefully grab that into there first. And close the latch on that socket. And this is awkward. But I'm trying to do it on the camera. There we go. Right, now with that ribbon cable connected, just carefully line up the IDC connector and then just push that in. Right, that's all done for that part. Next, the main front sensor cluster goes into the front housing and carefully pressed into the waterboard connector with everything all lined up. And now we can secure that in with these two screws. And finally, the battery. In case you haven't realised, that is to detect when the battery is overheating or not, beginning to fail, for instance. It's part of the battery management chip that's on the power board. It's a requirement, but I could have bypassed it with a 10k resistor, but I decided, given how cheap these are, just put it in there and it's a bit of extra level of safety. Now, just put the magnetic hatch back on and that's put back together. Now we're very briefly going to go over some of the changes to the code. Now I'm not going to go through absolutely everything because we'll be here for too long and this video is already long enough. I'm also suggesting that if you want to have a look at some of the code more in depth, to check out the earlier video for the previous version that goes through some of the parts more in depth. Some of the main changes here. Now obviously all the code from the previous version is in this. It may have been restructured a bit and tidied up in some way, but the vast majority of the code is still here. But it has been reorganized and split into header files and code files, and something I didn't do before. What this has helped me accomplish is also make a more efficient binary file that allowed me to basically put more program into the final package. Now anyway, let's get this startup routine and beginning out the way. Up here we have the main file, the main INO file in this case. At the top we have the personalization options. So for instance, in my case, Lieutenant Commander, Magnus Tyrannus, which is a play on Mangy Dog, and the serial number for my particular build. Now the reason why I've done this is because I've been making a few of these and people wanted personalization on their tricorders. This allowed me to quickly jump between each individual one to compile their builds. Those idents are obviously available if you press, long pressing the ident button displays that information. Normal startup stuff until we get to the tricorder begin. Now this is one of the major changes that happened. For starters, the tricorder class itself. I've reorganized a lot of the original code surrounding loading assets and displaying the pages, and that's now all inside the tricorder class. The reason why I've done this, it made things a bit better organized and a little bit easier to debug and figure out where things may have been going wrong. It also limited any kind of function conflicts that I was having before, as well as potentials for duplicate functions. I obviously gone through the code to try and remove as many that I may have had, particularly with the UI rendering function. So where I had to build up the scripts of kind of OpenGL code that the graphics chip uses to display the UI, I took out stuff that was essentially reusing the same functions and put them into a more homogenized list of functions that everything called for. So Tricorder I2C Begin, that is a reworked version of the wire library, and the reason why I did this was because when I was using the battery controller chip and the capacitive touch chip from the original version, the wire library that came with this is for the Roger Clark based Arduino core, had some problems. I think there was a weird conflict with how it addressed multiple addresses, not quite simultaneously, but in a staggered way. I had to rework the library for it to make it function, because the battery controller chip uses I2C and I needed to be able to talk to the chip, which is part of its function, which we're also about to have a quick look at inside the Power Begin. Now this is where the startup happens for the battery control chip. So for instance, these flags needed to be set in order for setting things like the current, the minimum voltage allowance, or even maximum voltage allowance, whether it's charging or not. These were also set in resistors, but part of the requirements for the chip is that it needs to be set in software as well. So there, these flags are set. This shipping mode function, well, the reason why this is needed is because shipping mode on this chip essentially disconnects the battery from the circuit. It's a great way of like isolating the battery, but in this case, if I'm running the tricorder in display mode, I don't need the battery connected. So what this does, it detects whether the power on is triggered by the power button itself, which in this case it's using the power latch IO GPIO pin, which is what that button is connected to as well. Detects whether the power on sequence has been triggered by the button or by power coming from the USB, and this basically sets that shipping mode, disconnects the battery if needs to, or keeps the battery connected. This then flips that power latch IO to an output and latches the IO, which was this case turns the DC to DC enable pin and holds it up in software. This is done physically when the button is pressed down. As I showed before on the schematic, it holds the enable pin up while the system starts booting, and of course this all happens, you know, within a couple of milliseconds, so to the user it's instant. After the enable pin is set up, it then runs through a quick block beep. Now the block beep is different from my normal beep. I've got two beep functions, one block beep and one normal beep. Normal beep uses the free RTOS thread to run a non-blocking beep that can traverse scheduling, if that's the best way to describe that. It means that I can run a beep and it would not interfere with anything else, and all the threads are running so quickly anyway that the time it takes for the beep to finish its beep cycle, say 20 or 50 milliseconds, it's due its threaded schedule anyway, and that would then disconnect the beeper in its timely manner. But this block beep is blocking code. It essentially just, you know, sets the IO high, runs a delay, sets the IO low, runs a delay. That obviously is blocking, but it's fine for this section of the program because the threads haven't actually started yet. But this is an indicator for me when I was debugging, but also for the user to know that their machine has started to turn on. The tricorder has started to turn on. Now this while loop is just waiting for the user to let go of the button. This section quickly fills up the array for the battery voltage level. This is just a quick startup array. It may be a bit rough, you know, there might be some noise in that, but it's enough to basically tell the tricorder and the user the fact that the battery's not low and about to shut down. So that's just a really dirty way of getting things working there. And it runs then a battery check, which does the check to see whether it needs to actually turn off because it's running low. Now, another block beep. That was more for me as a debug, just to know that it's getting through certain sections of code, which I did need earlier on, but not so much at this stage. Door serial, that is the that is the serial code that runs between the door and the main the main microcontroller. This uses an updated version of the frame serial library that I created a while back, fixing a few bugs, had a problem with the checksum before, which actually was just pure luck that it worked. But now it does work, and I've corrected that. I'll probably find more bugs again in the future, and that will just obviously be improved over time. TLC begin, that is the adjustable LEDs. All the LEDs themselves are dumb, but it uses the TLC 5940, 5947, I've forgotten now. The adjustable controller for all the LEDs, and that's just part of the routine that uses that. It's a single wire shift register type thing, very similar to other adjustable LEDs. Setting their brightness, clearing the LEDs, making sure it's turned off. And here is the main buts begin part of the sequence. Again, I added this if statement, so there's two potential addresses for the chip, and when I was debugging and trying to sort out problems with the board itself, this was able to tell me whether it was getting its signal to change the address or not, or if the chip itself just wasn't replying, so that's where the no TP comes from for that. Very, very simple, but just allowed me to debug and fix any issues that may have rose up per board as I built them. Because I was soldering some of it myself. Half of it was being assembled, and some of it was done myself. Display begin. This is again mostly the same as before, but slightly homogenized together, where this uses a SPI-like data bus to set the display and configure it for RGB parallel mode. This has to happen or the display just won't turn on. It's a pain in the ass because trying to find this information wasn't very easy, but I eventually managed to debug it, find some different sequence of codes, and then found the data sheet, and then just managed to cross-check everything and then build up the command list myself afterwards. That was actually done a long time ago, like a few years ago, but that's pretty much the same, as well as the setting of the chip itself. I'm using the Game Arena library still. I've tweaked it, but it's still that base library. I may move away from the Game Arena library soon, and just want to try and have a much more stripped down version that doesn't need a lot of the superfluous functions that Game Arena provides, which is great if you want to use them, but I don't need them. Start page is just setting the starting page, and the calibrate is if there is no calibrate if there's no calibration file on the SD card, it will then run the calibration. That is actually one of the other changes this version of the tricorder has. The calibration, rather than being stored somewhere inside a spare bit of flash of the microcontroller, I now put that onto a file on the SD card. That frees up more flash space for me to put more program onto the microcontroller itself, but it also means that if it ever becomes corrupted and needs tweaking, you could just delete that file off the SD card. And also apologise for the jets, we are in a RAF area. Coming out of the calibration screen, we then set the thresholds for the capacitive touch buttons, audio serial, which talks to the JQ8400 chip, and sets its volume, and then returns true knowing that it's got out of its begin sequence. And that bit was again just for me debugging to know that I've turned the thing on, it's got through all the sequences, it isn't got hanging anywhere, it's not stuck trying to contact a chip that isn't able to talk to, but as long as everything runs, it then passes through to here and then goes into the initiate thread. And this is where all the FreeRTOS threads start up their schedule. And the program does what it does. You see the loading screen, you see the beeps and the UI is rendering their things, and the tricorder is functioning as it should. As we are essentially using software to turn on the tricorder now, it's no longer literally like a flip button that powers it up and turns it off. The tricorder needs a shutdown sequence. It's not very complicated, but what it does, it's this case, when the power button is long pressed, I think for 2 seconds, it then runs the shutdown. which basically runs this sequence, turning off some of the threads. The reason why I've done the threads this way, it allows the threads to shut down themselves in a timely manner. They're not being forced to shut down like mid-sequence. They'll turn off once they've done their cycle. And then goes to set mode 250. Set mode is another version of set page, but without some of the other functions that are part of set page. Set page actually triggers set mode, but towards the end of its list. Well, what set mode does then goes to loads a shutdown page. If I can find it here, yep. Which is a very simple UI that just shows a countdown sequence, and then when the countdown hits 0, it triggers the shipping mode function of the tricorder library. And what that essentially does, it forces the chip to disconnect the battery from the system and powers off the tricorder. Now, the reason why it's in a while loop is because on rare occasions the data doesn't always get through correctly, and I found that the tricorder would just sit there turned on and not actually do anything, and the only way to turn on was to pull the battery out. The only way to turn it off was to pull the battery out. Putting this in the while loop makes sure that that data does get there and it forces it to turn off. This is all that's needed to turn off the tricorder. I don't need to disable the enable pin. It's just purely done via this mode. I had the code use the enable pin before. It probably isn't necessary now. It's only because I thought that maybe that I may require it in the future. That was just me sort of covering all the bases when I was designing this version of the tricorder. I may still use it in the future version, I may not, I don't know, because this is enough to just turn off the tricorder. And like I mentioned, everything now is homogenized into a tricorder class itself. This allowed me to organize the software better and to make sure I didn't have like too many superfluous or duplicate functions trying to do the same thing in their own different way, which has actually caused some problems in the past. But this is fine for this version of the tricorder. Now we're coming to the end of the video. I wanted to talk a little about what's happening with me and the YouTube channel going forward. First and foremost, as I have already said, I have just lost my dad to cancer, and after already losing my mother to cancer 7 years ago, this has of course hit me really hard. Losing both my parents at a relatively young age has left me in a really uncertain position, given that I am still unemployed and finding it difficult to get back into work. As we are dealing with my dad's affairs, it is clear that we have no choice but to sell our home. This means that for the next few months things are going to be really chaotic, as I first need to find a new place that I'm able to afford after my dad's debts have been settled. I also then need to move there. As you can imagine, there is a lot of uncertainty going forward, and because of this I can't say when my next video or project will be released. However, I did want to give you some good news and let you know of some of the planned projects coming up. This isn't a sponsored segment, just some good news. Firstly, I want to give a huge thank you to PCBWay, who have approached me for sponsorship on my projects going forward. This will include some very expensive projects that I wouldn't have been able to afford if I was to pay for everything myself. So, you'll be hearing a lot about them in my future videos. While I'm not in the YouTube business to advertise, I will always give my honest opinion on any tech or service I use. Having a sponsor like PCBWay, who would not only build my PCBs but may also provide other maker services, would cut the cost of my projects, which would greatly help me. And like I said, I do have some very expensive projects coming up. Some of these include a new version of the retro gaming handheld with an RK3588 single board computer, a Star Trek Prodigy inspired tablet using the same RK3588 SBC, an ebook reader also using that SBC, a smart speedometer for a sports bike using that same SBC module as well, and of course the single board computer carrying out RK3588 that all these projects will use. I am currently designing a modular CM4 style board that will carry the RK3588 SoC that would fit into all these projects and more. And while it's still very early days, PCBWay have offered to build and assemble this board for me, though I will still be providing and paying for the parts. This is of course an expensive series of projects, and it wouldn't have been made possible without PCBWay's support. Another upcoming project that PCBWay have offered to support is the RGBW Studio Lite. I actually already had the PCBs for this project made, and they have been sitting on my shelf for over a year. This tricorder run really did take up all my time. However, there are some minor changes I wish to make, namely a slight reorganisation of the controls, so PCBWay have offered to do that for me too. And of course, the working Stargate miniature, which has become the bane of my existence, which must get some work done to it. And the first contact ball cube studio scale model, which I am very eager to get started with. I also have several other numerous projects on the back burner, so of course, if you haven't already done so, subscribe and click the bell icon to be notified when these videos come out. Even with the amazing help from PCBWay, my projects are not cheap for me to make, and many of them could not be done without the amazing support I have got through Patreon. The money raised there really does go straight towards the parts and materials I use. In fact, I am currently halfway through saving up for many of the expensive parts needed for the RK3588 single board computer project. If you want to help support me, consider signing up to my Patreon, or if you wish to make a one-off donation, you can do so through my GoFundMe. Links are in the description. Again, thank you for your time, and I hope you enjoyed this project. Stay safe, take care, and until next time, goodbye.